The vertical line test comes directly from the definition of a function. Remember, the definition of a function is it's a set of ordered pairs, inputs and outputs. It's a relation in which no two different ordered pairs have the same first coordinate. Remember that? Well, that definition translates directly to the vertical line test. So you could state the vertical line test this way. If any vertical line, what's a vertical line? Up and down versus side to side, right? It's like a vertical blind, right? If any vertical line passes through the graph of a relation, remember a relation can be thought of as a listing of ordered pairs, but also an equation with two variables. If any vertical line passes through the graph of a relation at more than one spot, in other words, at more than one point, then the relation is not a function. If any vertical line passes through the graph of a relation at more than one point, then the relation is not a function. And the easiest way to help you comprehend that is with an example. What do you think? Is the picture in part A, does that represent a function? Is it a set of ordered pairs? Yeah, any curve is a set of ordered pairs because it's comprised of ordered pairs. Now, it's comprised of an infinite set of ordered pairs because between any two ordered pairs you can fit another one. But any curve is a function, or is a relation rather. But is it a function? That's the question. What do you think? No, it doesn't. First of all, it doesn't pass the vertical line test. Let's show you that it doesn't pass the vertical line test and then relate the vertical line test to the definition of a function. If you can take any vertical line, doesn't matter which one, and show that it passes through more than one point, then it's not a function. So this is the work you need to show. It only takes one vertical line to show it's not a function. So draw the vertical line, highlight the 2 points that it passes through, and say, not a function. Oh, you need explanation. So the explanation to this reasoning that it's not a function is the vertical line test. So if you want to shorten that, you could say by VLT, vertical line test. Now, I want this test to make sense to you. I don't want you to just memorize it. So think about what this vertical line is doing. It's saying that this x value right here is going to not only this height, right, on the graph when you look at this associated ordered pair, but it's also going to this height on the graph. It's going to so a y value down here, call it y1, a y value up here. This one x value is going to two different y values. Not a function, right? You can't have a single x value with two different outputs. Okay? So that's where the vertical line test comes from, just the definition of the function of a function. What about in part B? Yeah, it's definitely a function. I mean, you could try drawing. What I would do here to show your work, just try drawing. You can't draw an infinite number of vertical lines, so just draw a few of them and say it's clear that any vertical line is only going to pass through one point. You don't even need to say that. You could just say, a picture says 1,000 words, right? So draw a few vertical lines. It's clear that any of these vertical lines, any vertical line you draw only passes through one point. So that, yes, it is a function by vertical line test. So that's all the work you need to show. Yes, it is a function by VLT. Okay? Yes?
So there you were saying that it's not a function because the x values, there's only one x value and there's two different y.
Let me put it another way. If you look at this point and this point, they're both on the graph, right? So they're both part of the relation. They're both ordered pairs in the relation, right? But they both have the same first coordinates, don't they? So can't be a function. Okay, you guys, a function is defined as a set of ordered pairs in which no two different ordered pairs have the same first coordinate. So there's no reason why you couldn't graph the function in the Cartesian plane. using, say, an x-axis that runs horizontally and a y-axis that runs vertically. So in this example, for this graph, let's find f of 2. Okay, so wait a minute. That's function notation. What does f of 2 mean? When you see generically y equals f of x, what that notation means, it doesn't mean f times x. You say this f parentheses x as f of x, and it's understood then that the x, whatever x is standing for, is the input that you plug into the function. If you think of the function as a set of ordered pairs, it stands for the first coordinate, and y stands for the output or the second coordinate. So if we want to find f of 2, we want to think about, okay, 2, that's where the x was over here, right? 2 has got to be the input. What's the corresponding output? Well, that's going to be the second coordinate of any ordered pair with a first coordinate of 2. If it's a function, there's only going to be one ordered pair with a first coordinate of 2. So input values are going to appear on the horizontal axis. Independent variable values, x would be the independent variable here, appear on the horizontal axis. Dependent values appear on the vertical axis. So just go over on the horizontal axis, in this case the x-axis, go over a distance of 2. Oh, okay, here's 2 on the x-axis. Now what's the corresponding y-coordinate? 1, 2, 3, 4. Okay, so that means f of 2 must equal 4. And that's it. That's the answer to part A. Another way to think of that is that the ordered pair 2, 4, this guy right here, is on the graph of f. So what's the domain? Well, remember, the domain is the set of all values that x can take on, or that input values can take on. X doesn't have to represent input values every time. So when you define a function as a finite set of ordered pairs then, or as an infinite set of ordered pairs, the domain would be the set of all first coordinates of those ordered pairs. So look, going from left to right, it's nice to write it in order. The domain value of this point right here will be negative 1, 2, 3, 4, 5. So the domain is going to start at negative 5. The domain value of this guy will be negative 4. And then it's going to go negative 3, negative 2, negative 1, 0, 1, 2. So it's going to go negative 5. Just list them. It's a finite set of ordered pairs. You can list them all. It's not even a very big set of ordered pairs. So there's no reason why you can't list them all. So negative 5, negative 4, negative 3, negative 2, negative 1, 0, and then 1 and 2. And we're going to use what a lot of books call set roster notation with just the curly brackets. When you list all the entries in a set, use the curly brackets. Okay, for part C, we're asked to find any x value or values, I put the s in parentheses, such that f of x is equal to 3. So here we're going the other way around. We're given an output value of 3, a height value of 3. And we want to find any input values that correspond with a height value of 3. Okay, since it's this function's a finite set of ordered pairs, this is equivalent just to finding all the ordered pairs that have a second coordinate of 3 and then listing their first coordinate values. So go up to a height of 3 on the graph, 1, 2, 3, and then go over left, right to any points at that height. So this point and this point have second coordinates of 3. And all we need to do is list their first coordinates. Those will be the x values we're looking for. So the first coordinate or x coordinate of this point is at, I believe, negative 5. 1, 2, 3, 4, negative 5. So negative 5 is one value x could equal, but also x could equal, what's the x coordinate of this point? First coordinate of this point's 1. So x could also equal 1. So those are the two first coordinate values or input values or x values, whatever terminology you want to use, such that you plug those in as inputs to the function. The output is 3. In other words, those are first coordinate values that correspond with second coordinate values of 3. And then finally, the range. Okay, for the domain, in part B, for the domain, we think, okay, left to right. What are input values that correspond to points in our picture, in our graph here? For the range, so we thought of x coordinate values for the domain in part B. For the range, let's think of height values. The domain is all the inputs that the function can take on. The range is the set of all outputs given that set of inputs. So what are all, that breaks down in this question is just answering, what are all the second coordinate values of these points? Well, they repeat, and that's okay for second coordinate values to repeat, but there's a point at a height of 0, 2 points at heights of 1, 2 points, and it doesn't matter that there's 2 points. It just, the function reaches a height of 1, of 2, of 3, and 4. And those are and 0, don't forget the one at 0. So those are the only values that the range can take on. 0, 1, 2, 3, 4. We'll use set notation for that. So curly brackets on the end. Separate those entries in the set by commas. And you're done.